Hello guys, in the last lecture what we covered was, we saw the parallel operation of transformer. So first of all we saw the necessary condition for parallel operation. What were the necessary conditions? Same voltage rating, then same polarity to avoid any circulating currents, then same phase sequence, and at last same phase shift between the primary and secondary. These were the necessary conditions that we saw for the parallel operation of transformer. And then we saw how the load is shared between two transformers. There we saw SA was equal to SL ZB by ZA plus ZB conjugate, and SB was SL ZA over ZA plus ZB conjugate. So we saw that loading is inversely proportional to impedance. Okay, and here ZA and ZB were to be taken in ohms or per unit but on the same base. So in this lecture we will be covering one other type of transformer, that is called as auto transformer. Okay, now here auto transformer, please do not confuse the definition by the transformer that is used in a auto, because I have heard many students that auto transformer means the transformer that is used in a auto. It is not like that. Auto transformer is a special type of transformer in which primary and secondary winding are not isolated from each other. When we studied two winding transformer or the normal transformer, there we saw primary and secondary did not have any connections. How they were wounded? On this limb we had on the left limb we had a primary winding, and on the other limb we had a secondary winding. They were magnetically coupled to each other, but they did not have any electrical connections. That is, current does not flow from one winding to the other. Okay, only EMF can be induced from one winding to the other, or current can be induced, but current cannot be conducted. But in case of auto transformer, what happens is, suppose this is my core material, how the winding will be wound? Something like this. So this will be my primary side. This is my secondary side. So some portion of the winding is common between primary and secondary. Such kind of transformer is called as a auto transformer. Okay. So here, since some part of the winding is common between primary and secondary, some current will be flowing from primary to the secondary winding. That is, there is conduction between primary and secondary. As in case of normal transformer, here also we will have induction between primary and secondary, but due to common part of the winding there is also conduction. So here we have induction as well as conduction. So there are two mechanisms for the power transfer in case of auto transformer. One is by means of induction, other is by means of a conduction. Okay, and here we define the transformation ratio. Transformation ratio is defined by K. It is written as low voltage by high voltage. Okay, transformer will have two windings, that is low voltage winding and the high voltage winding. The ratio of two will be called as a transformation ratio. Okay, remember this point. Here we are not considering primary or secondary. I am just saying low voltage upon high voltage. So how is auto transformer different from a two winding transformer? Here some part of the winding is common, so there is induction as well as conduction. Now why should we go for auto transformer? What is the problem with the two winding transformer, or what are the advantages of a auto transformer? Now as we saw in just the last slide, that the two windings were wound on the same core or the same limb, and there was some portion of the winding that is common. So here core volume is less. Since we do not require two limbs to wind the windings or to wound the primary and secondary, so the core material required is lesser as compared to a two winding transformer, because now even a single limb can function as well as the two winding transformer. So core volume is lesser, that means cost will be lesser. Okay. Next is, since core is lesser and since we are not isolating the windings from each other, we need no insulation. Okay, since there should be conduction between two windings, so there should be no insulation between windings. Okay, if there is insulation between the windings, then current cannot flow from one winding to the other. That is why we need not provide any insulation. That is why the cost will reduce further. Okay. Now size, weight and cost reduce. Size reduce because core volume is lesser, weight is reduced because core volume is lesser, and cost is reduced because no insulation is required and core material is also less required. Now here some part of the winding is common between the two windings, so that means we need less amount of copper. Earlier primary and secondary windings were separate. Now secondary winding is a part of primary winding. So number of turns or the winding copper is less. Okay. Earlier we had to create two windings. Now one winding is created out of other. So we need less copper material. Now since core is lesser, copper is lesser, that means we saw core losses is proportional to core volume. So core loss will reduce. Since copper is lesser, copper loss will also reduce, which means higher efficiency. So remember, auto transformers always have higher efficiency as compared to the two winding transformer. But whenever the transformation ratio is less than 1/3, then auto transformers are not used. Okay, it is not that much economical to have a auto transformer when the transformation ratio is less than 1/3. Auto transformer is not feasible at such a transformation ratio. Now let us see how currents and voltages are divided in a auto transformer. So let me first draw an auto transformer. This will be my auto transformer. Suppose this is N1 number of turns and this is N2 number of turns. Now assuming that current flowing here is I2, current coming here is I1. So current going here would be by KCL I1 minus I2. Okay, at this point if we apply KCL, current I1 is incoming, I2 is outgoing, so other outgoing current will be I1 minus I2. And these terms would be N1 minus N2. Okay. Here I am assuming a voltage V2. Here we can assume a voltage V1. Okay. Now this part of winding is common. The N2 number of turns is common between primary and secondary. So whatever is the power in these N2 number of turns would be conducted power, because whatever the winding is common transfers the power between primary and secondary by means of conduction. Okay. So that means conducted power would be how much? The voltage across this winding is V2, current is I1 minus I2. So this is the amount of power that is conducted. Okay. So rest of the power is induced. Whatever the power is across this part of winding is not directly being transferred to the secondary. It is being transferred to the secondary by means of induction. Okay. Induced power would be the voltage across this is V1 minus V2, current is I1. Okay. So conducted power is the power across the common part of the winding, and induced power is the power across non-common part of the winding. because whatever power is in the non-common part cannot be directly transferred to the secondary. It has to be transferred by means of induction. Now total power on primary and secondary must remain same, because as I told earlier also, transformer does not work as an amplifier. Power must remain conserved. V1 I1 is equal to V2 I2. Now if we divide induced power by total power, V1 minus V2 into I1 by V1 into I1. So this is 1 minus V2 by V1. Okay. Now if you see, V2 has lesser number of turns, that means it is a lower voltage. V1 is across N1 turns and V2 is across N2 turns. That means V2 by V1 will be termed as low voltage by high voltage, which is my transformation ratio. So what I can say, induced power is equal to 1 minus K times total power. Okay. And conducted power would be total power minus induced power, that is equal to K into total power. So that is how the power is being transferred by two mechanisms. One is by induction and one is by conduction. Okay. So 1 minus K times total power will give me induced power, and K times the total power will give me conducted power. Now copper weight in auto transformer is 1 minus K times copper weight in two winding transformer. As I told you, less copper is required, so the ratio of copper required in two winding transformer to the copper required in auto transformer is 1 minus K. Similarly, full load loss in an auto transformer is 1 minus K times full load loss in two winding transformer. Okay. Similarly, voltage drop. Now since copper requirement is less, that means winding resistance will be less, and since winding resistance is lesser, the voltage drop will also be less. So percentage voltage drop in auto transformer is 1 minus K times percentage drop in two winding. Okay, because the copper requirement is lesser, so resistance of the copper winding will be lesser, so voltage drop will also be less. Next is kVA rating. This is the most important of auto transformer, is 1 upon 1 minus K times kVA rating of two winding transformer. This point is most important. And always remember, full load losses are scaled by 1 minus K times, but if a question or a problem is asked on the efficiency, then if we cannot separate between core loss and copper loss, we will assume the losses as constant, because here we are only scaling the copper losses. So if you have copper losses separately, then you must scale it by a factor of 1 minus K. But if you are given a total amount of loss in which you cannot separate between core and copper loss, then assume losses remain same between two winding and an auto transformer. This point must be kept in mind. Losses must be considered same between two winding and auto transformer while calculating the efficiency. Now let us see how we can realize a auto transformer. So what I have been given here is a two winding transformer, and we need to construct a auto transformer using this transformer. Okay, here the power rating is 20 kVA. So rated current on primary would be 20,000 by 2000, that is 10 ampere. Similarly, rated current on secondary is 20,000 by 200, which is 100 ampere. So here I have shown the different currents flowing in the windings and what are the voltages across the winding. Now to construct an auto transformer out of this two winding transformer, we need to connect the two windings. Okay, because some portion of the winding must be common between the primary and the secondary. So there are two ways to connect the windings. The first way is called as additive polarity. What do you mean by additive polarity? Is the windings are connected in such a manner that the voltage across the windings is added. If you see here, the total voltage that is coming out to be is 2200. 200 plus 2000, that is 2200. So windings are connected in a additive polarity. Now we have seen in the secondary winding, that is a 200 volt winding, the current flowing is 100 ampere, that I showed you in the last slide. Here the current is 100 ampere. And in 2000 volt winding, it is how much? 10 ampere. So if we apply KCL, here the current coming would be 110 ampere. Now if we want to find the KVA rating, S auto, the voltage across is 2200 into 100, that is 220 KVA. Okay. Otherwise you can calculate from primary also. It is 2000 into the voltage across is 2000 and the current coming here is 110. So it is also 220 KVA. Other way is to calculate using the transformation ratio. K is low voltage by high voltage. Here the low voltage or the primary voltage is 2000 volt. Secondary is 2200 volt. So it is 1 by 11 or 1 by 1.1. Okay. Now I told you auto transformer rating is 2 winding KVA divided by 1 minus K. It will come out to be 220 KVA. Okay. There are three methods to calculate the KVA rating of the auto transformer. One is using the transformation ratio, that is auto transformer KVA rating is 1 upon 1 minus K times the KVA rating of 2 winding transformer. Other is to multiply the voltage and current across the secondary, and the third method is to multiply voltage and current across the primary winding. Okay. So these three methods can be used to determine the KVA rating of auto transformer. Now let us find what portion of this power is conducted and what is induced. We need to find the conducted and the induced power. Now conducted power is the power across the common winding. Conducted power will be, as we derived the expression, K into total power. The K was the transformation ratio, which is 10 by 11 or 1 by 1.1. Total power is 220 KVA. Now this will result in how much? 200 KVA. This is the power transferred through the conduction phenomena. Then induced power would be 220 minus 200, that is 20 KVA, which is same as the rating of 2 winding transformer. So the rating of 2 winding transformer is actually the power that is induced from the primary to secondary, and rest of the power is transferred by means of conduction. Okay. So remember this point. Next, let us see what is the effect on efficiency by converting the 2 winding transformer to a auto transformer. So I am assuming 2 winding transformer had an efficiency of 98% at full load UPF. So eta is 0.98, which means P out is 20 into 10 raised to the power 3 into 1. 20 into 10 raised to the power 3 into 1. Here what I have done is I have converted into real power using S cos phi. S is the KVA rating. Cos phi is 1 because it is given at unity power factor. Plus losses. So here we can calculate the losses. The losses will come out to be 408 watt. Now as I told you, consider the losses as constant whenever we are making an auto transformer out of a 2 winding transformer. So if we calculate eta auto transformer for full load unity power factor, The kVA rating is 220 kVA and I am considering unity power factor. 220 kVA plus 408. Okay, this comes out to be 99.8%. So now if you see, the efficiency of a auto transformer is much higher as compared to efficiency of a two winding transformer. Okay, this you must always keep in mind. The efficiency of a two winding transformer is always lesser as compared to auto transformer. And consider the losses as constant whenever we are realizing a auto transformer from a two winding transformer. Now other means of connection could be such that the voltages are not added but rather voltages are subtracted. That is called as subtractive polarity. So here I have connected it in such a manner that plus minus 200 is like this and minus plus 2000. So net voltage would be minus plus 1800 volt. So now 2000 and 200 are being subtracted. It is called as subtractive polarity. Now we know the rated current in 200 volt winding is 100 ampere and we know the secondary side should always deliver the current. So current must enter from negative terminal and current must leave the positive terminal like this. Okay, current cannot leave the negative terminal, otherwise the secondary side would be delivering the power, not at all absorbing the power. On the secondary side I have connected a load, so it must absorb the power. That means the current should leave the positive terminal. That is why 100 ampere will be like this and here 100 ampere will be entering. Now 100 ampere is coming like this. So 10 ampere will be like this. In 2000 volt winding the 10 ampere should be like this. Why is it so? Because in a transformer one thing is for sure. One current enters the dotted terminal and other current leaves the dotted terminal. Let me show you. Suppose we take a two winding transformer. This is my dot. It is primary winding, it will absorb the current. This is secondary, so it will deliver the current. So here current is entering the dotted terminal, here current is leaving. So in this diagram if you see, current is entering dotted. So this dot current must leave, current cannot enter. So 10 ampere current should be downwards. Always in a transformer, current enters from one dotted terminal and leaves from other dotted terminal, because primary and secondary MMF or flux should oppose each other in accordance with the Lenz law. Okay, according to Lenz law they must always oppose each other. Now by KCL what I can say? Current going here will be 100 minus 10, that is 90 ampere. Okay. Now if we want to find out kVA rating of auto transformer, it is 1800 into 100, that is 180 kVA. Okay. Please do not apply those formulas that we have studied, that is 1 upon 1 minus k for subtractive polarity. Rather keep those to only additive polarity. Whatever formulas that we studied, that kVA of auto transformer is 1 upon 1 minus k times kVA of two winding. Do not apply those to the subtractive polarity. Keep those formulas only up to additive polarity. So here we have to find auto transformer kVA rating conventionally, that is voltage into current. Okay. Now we want to find the induced power and the conducted power. As I told you, induced power will always be kVA rating of two winding transformer, that is 20 kVA. So kVA conducted would be 180 minus 20, that is 160 kVA. Conducted power would be 160 kVA and induced power would be 20 kVA. Now let us again try to calculate the efficiency. Again we will assume eta 2 winding is 98% at full load unity power factor. From here we calculated the losses as 408 watt. Now if we take eta auto, the power is 180 kVA, 180 into 10 raised power 3 into unity power factor 1, 180 into 10 raised power 3 plus losses are 408 watt into 100%. So this comes out to be 99.77%. So here also we can see, even in a series subtractive polarity, the efficiency of auto transformer is way higher than the two winding transformer. It is pretty close to the 100%. So remember, auto transformers are used as step up or step down transformer, which is cheaper in nature. Okay, because here the ratio of voltages is higher. So that is why we can use it for step up or step down applications. And here the cost is low, efficiency is high. Okay. Now let us see a similar concept to the two winding transformer. What happens if we refer the impedance from secondary to primary or from primary to secondary? So let us take an auto transformer. Okay, here we have N1 number of turns, here we have N2 number of turns. This is N1 minus N2. Okay, this current is I2, this current will be I1. Here the voltage applied would be V1. Now what to do is, to find the referred impedance or to find the equivalent circuit, what we will do is, we will analyze the auto transformer as a two winding transformer with a primary winding having N1 minus N2 number of turns and secondary having N2 number of turns. So this will be analyzed as a two winding transformer with turns ratio N1 minus N2 is to N2. Now if we take this point as A, this point as B, what we can write? VAB is equal to induced EMF, that is E1 plus I1 into R1 plus J X1. Okay, similar equation to a normal two winding transformer. Now we know the induced EMF will be in the ratio of N1 minus N2 by N2, because we are analyzing it as a two winding transformer having a turns ratio N1 minus N2 is to N2. We are not considering the conduction. So we can write as VAB is equal to E1 can be replaced by N1 minus N2 by N2 into E2 plus I1 into R1 plus J X1. Now this E2 can be written in terms of V2 as E2 is equal to V2 plus I2 R2 plus J X2. Now we know in a two winding transformer, primary and secondary MMF are equal. That is N1 minus N2 into I1 should be equal to N2 into I2. So we can write E2 as V2 plus N1 minus N2 by N2 into I1 R2 plus J X2. Now if we substitute this E2 in VAB, VAB is N1 minus N2 by N2 into V2 plus N1 minus N2 by N2 square I1 R2 plus JX2 plus R1 plus JX1 into I1. Now if we take I1 common, what we will get is R equivalent would become R1 plus N1 minus N2 by N2 whole square R2, and X equivalent would become X1 plus N1 minus N2 by N2 square X2. Okay, similar to the two winding transformer but with a turns ratio N1 minus N2 is to N2. So that is how we transform the impedance from the secondary winding to the primary winding. Okay. So this is all about the auto transformer. What points you have to remember here is, one is the rating of the auto transformer, how to design the currents in different parts of auto transformer and find the rating. Second is how to find the efficiency, that is you have to consider the losses as constant between two winding and the auto transformer and then find out the efficiency of the auto transformer. So these are the steps involved while solving any problem based on auto transformer. And why auto transformer is used? Because it is used for step up and step down application, which has a cheaper cost and higher efficiency. Now let us summarize what we have covered in this lecture. We first saw auto transformer, why it is used and what is the difference. The difference is there the two windings are not isolated, but rather they have some common portion between the two windings. Next, what we saw, in an auto transformer, the power is transferred by two methods, induction and conduction. Induction was K times total power, 1 minus K times total power, and conduction was K times total power, where K is transformation ratio, low voltage by high voltage. Then we saw efficiency, or we saw KVA rating. KVA rating was 1 upon 1 minus K, KVA rating of two winding transformer, and based on this information we calculated the efficiency. We saw two type of polarity, additive and subtractive polarity, where secondary voltages are added or subtracted based on their polarity. And last we saw the equivalent circuit, that is how to refer the secondary impedance to the primary. So we multiplied it by a factor of N1 minus N2 by N2 square. Okay. In the next lecture we will see some problems based on parallel operation and the auto transformers.